All right, everyone, welcome to this presentation on geologic time. Let's get right into it. First, to understand geologic time, we got to understand how geologic time is measured. So, the first way that scientists measure it is with relative time or relative dating. It's a measurement of rocks and the sequence in which they were laid down. So, intuitively, we know that older rocks will be lower in the Earth's layers. And here you have a picture from the Grand Canyon. You can see that the older rocks are on the bottom and the younger ones are on top. And these inferences are made at rock outcrops, which are exposed rocks at the Earth's surface. The Grand Canyon is one of the most well-studied and best places to research and date rocks in terms of relative dating because of how these rocks are exposed. And that's actually where this picture was taken. And the other form of dating is called absolute dating, which is a lot more precise, and it measures when events took place, and it relies a lot on a process known as radioactive dating through radioactive decay, which we'll talk a little bit more about later on. And these two types of dating, they're really used in tandem with one another to formulate a more complete picture of geologic time. So let's first cover a little bit of history of geologic time. It started with this guy named Archbishop Usher and his principle of catastrophism, who used the Bible to date the Earth. And the Bible, if you ever read it, it has a bunch of genealogies in it after the creation story with how long people lived. And if you take all those genealogies and those lives and you add them all up together, you get an Earth that is about 6,000 years old. And if it's only 6,000 years old, this guy Usher said that there's no way that rivers and streams could have formed all these rock structures, these giant rock structures. It had to have been through catastrophes, which is where the principle of catastrophism gets its name. And this was a prevailing theory in Europe, the center of world academia, for over 200 years, until the Neptunists came along with their theory of Neptunism, which is the belief that the whole Earth was covered in water. And it wasn't until this water kind of receded away that layers of sediments that were laid down, that they began to be exposed. And those were the rock structures that we now see today in modern times. It was actually the wrong theory, but it was the first to challenge the idea that the Earth was 6,000 years old. And the Neptunists were in contention with the school of thought known as Plutonism. And it disagreed with the water theory, noting that certain types of rocks, they couldn't form as precipitates of water. Chemically, it was impossible. So a rock such as granite can actually only be formed through the crystallization of, you guessed it, magma or molten state rocks. So it was really the Plutonists who pushed forward into modern geology, and we can't really talk about modern geology without James Hutton, who is the father of modern geology. And he proposed a theory of gradualism, and it was through his book in 1795 that detailed the theories that he proclaimed. It was called the theory of the Earth, and he said that it was different forms of weathering and erosion that were the engines over time that led to the current rock structures. Different weathering and erosion, such as water or earthquakes or any number of things. And his example was Hadrian's Wall, which was a wall erected between Scotland and England by the Roman Empire. It was erected in AD 122, and by the time he started publishing works 16 centuries later, Hadrian's Wall had seen almost no erosion whatsoever, and it had spanned almost a third of the Earth's what was believed to be a 6,000-year existence, and it hadn't seen almost no erosion at all compared to some of the rock structures they observed. And it was using these two observations in juxtaposition to one another that really allowed the thought to push forward that, hey, this Earth is a lot older than 6,000 years. And it was Charles Lyell who built upon the theories of gradualism and formed the theory of uniformitarianism, that it was the same geologic processes that have worked at the same level of intensity spanning all of time. He was the first one to say that the present is the key to the past. So processes that we see occurring in the present, they tell a lot about the same process that have occurred in the past. And he didn't rule out catastrophes, but he just considered them a part of these geologic processes that had been at work for millions and what they came to know billions of years. So let's talk a little bit more about relative dating and Steno's rules. We have the law of superposition, which is that the oldest rocks are on the bottom, youngest on top, quite intuitive. The law of original horizontality, which is that as rock layers are laid down, they're laid down one on top of the other in a parallel way. And the law of lateral continuity, which is these rock layers are laid out over very large areas, and it was all continuous. And when these rock layers were laid down, it was one continuous layer after another, and only until later do you see them begin to split apart through different kind of processes like the movement of plate tectonics. You also have the rule of cross-cutting relationships, which is that any intrusion of one rock or kind of a dike of rock, it cuts across different layers of rock, and any intrusion that cuts across layers of rock, it has to be younger than the rocks it cuts across, which is not to be confused with the rule of inclusions, which is that the fragments within a rock layer, they must be older than the rock layer itself, which makes a lot of sense intuitively. The cross-cutting relationships are different because these things are formed through perhaps like a magma plume that forced its way through certain layers of rocks, whereas the rock layers themselves, especially the sediment ones, they're composed of different fragments of other rocks, and it only makes sense that those fragments are older than the rock layer itself. So let's talk a little bit about the unconformities. And the most basic one is a disconformity. As you can see, it's just different layers of rocks or different layers of sediments laid down one on top of the other. There's the angular unconformity, which is rock layers that are laid down, and before new ones are laid down, they experience tilts and shifts through the movement of plate tectonics or other types of erosion. And then the nonconformity is a little bit different because it's not layers of sediments laid on top of one another, but it's actually layers of sediments laid on top of a layer of igneous rocks, which are laid down by molten or lava or volcanic explosions or volcanic runover that exposes some of the molten state rocks to the surface of the earth. So with all that down, let's get into the geologic time scale. We have here eons, which span billions of years, and this super eon is the Precambrian, which actually encompasses the first 3 eons. And we have here that there are 4 eons total, and life doesn't start showing up around until the Phanerozoic eon, which again spans billions of years, but there's eras contained within eons that span several 100 million years. In the Paleozoic, it means ancient life, and then we have the Mesozoic, which means middle life, and the Cenozoic, which means modern life or contemporary life. And it wasn't until the Phanerozoic eon that we saw this type of life, of advanced single cell and then multicellular organisms come along. And just a quick fun fact in the Mesozoic is actually when the Jurassic period was. Periods spend tens to about 100 million years, and the Jurassic period was actually when dinosaurs ruled the earth and they covered the earth. And the Cenozoic, we're getting a little bit closer to when humans started showing up, but we're not quite there yet. In the Cenozoic, you see a couple of periods which are broken down into epochs, and epochs span tens of millions of years. And interestingly, it wasn't until the most recent epoch, the Quaternary period and the Pleistocene epoch, which predated the Holocene epoch. And you can see now that the Holocene epoch, it really only shows a very, very small portion of this entire geologic time scale. And you may be depressed or just astounded to know that humans did not even exist until the Holocene epoch. So yeah, that just puts into perspective how big this geologic time scale really is. So let's talk a little bit more about absolute dating and the radioactive decay. So the way that scientists take rocks and they date them is they take a rock fragment and they look at the isotopes within them. An apparent isotope is made up completely of unstable atoms. And these unstable atoms, they're called parent isotopes, they break down into stable daughter isotopes. And so when you take a rock fragment that's fully parent isotopes and you wait for half of those parent isotopes to convert into daughter isotopes, meaning you have half and half, that is called one half-life. And scientists can tell how long these half-lives are. And when they get a rock fragment and they measure the ratio of parent to daughter isotopes, or parent to daughter atoms, then they can tell how many half-lives have gone by. And if they can tell how many half-lives have gone by and they know how long the half-life of that particular element is, then they can tell exactly how much time has passed since these rocks they were formed. And if you want to know a bit more, then it's quite a bit more complicated than the shortened version I just gave, but you should look it up online. And a few of the elements that are really commonly used in this process of dating are uranium, lead, rubidium, strontium, and potassium argon. And the international commission that puts together this geologic timescale is the Commission on Stratigraphy. It began in 1974, and they really set out to create a standard by which a bunch of scientists could work by and collaborate on the geologic timescale. And it's governed by its more well-known parent organization, the International Union of Geological Sciences. And together they've standardized a lot of terms in the geologic timescale so that people like us could create presentations like this, and I hope this helped.